So welcome back, everybody. Before we dive into this week's topic, I wanted to guide the eye with respect to what is coming this week and next week. So the aim today is to start, getting started with the programming of neural networks. And I want to show you how you can actually implement it. Then last week in these exercises for week 41, the thing which was the main task was to set up what we call the forward step, the feed forward step in a neural network. So that means that you send through the input, the network then modulates the input and produces an output, which is then compared with the target values. Then you optimize at the endpoint the cost function with the output of the network. Then you use the chain rule for derivatives, find the gradients. That is the back propagation algorithm, which essentially is you finding the gradients. And then you use a gradient descent to update the parameters. And then you step yourself back till the input. Then you have updated the parameters once. Then you go through the network again and back and forth till the cost function which you have defined doesn't change by some given parameter by you. So one thing could be the accuracy of the calculations. Then you could decide that I want a perfect accuracy, and then you can keep training till you get that or something close to it, etc., etc. So the exercises this week is essentially you setting up the back propagation path. So if you combine the exercises from last week with the exercises from this week, you have the backbone or the main part of a neural network code. Now, we are spending some time in project 2 on actually doing that, essentially because in that way, you're going to demystify what is at the heart of most deep learning methods. So whether you're doing discriminative methods, which will be the main focus in this course, or you do generative methods, which is more the topic for advanced courses, or you're doing reinforcement learning, there is always a deep neural network at the heart of everything you're doing. And that's because you often have to parameterize something which is given by a nonlinear function. And then a neural network using the universal approximation theorem is something which allows you to approximate a more complex function. Now, project number 2 deals with you reusing the gradient descent machinery from project 1 to a classification problem and a regression problem. Now, the project, I don't know if you probably haven't had much time to look at it, because this is something which we will also discuss a little bit more at the lab sessions, but you will find everything if you now scroll down along the Jupyter book. You will find obviously the lecture notes for this week. You have the exercises from last week if you didn't have time to do them, and then you have this week. And then in the project, we are going to make some small additions, which are going more to highlight what we expect from you. So at the end of the project, you will find some bullet points on the things we want you to do in project number 2. So that when you read the text, sometimes it's not easy to see the wood for the trees. Hopefully the bullet points at the end, which we will add later today, will guide you through what we think you should do in project number 2. So with that, when you have such a neural network code, one of the topics which we will discuss next week is how we can use neural networks to solve differential equations. And this is a field of applications which has really taken off and shows great promise, especially when you're going to high dimensional problems. And you will encounter the applications of neural networks in, for instance, the studies of turbulence, which has been a big problem in meteorology. So the applications of neural networks are really, really many. And the reason why we want to have you to write such a code from scratch is simply because we want to demystify what enters. So that means that you see the pros and cons, you see the bottlenecks, and you see how you can improve upon it. Okay, So that's a kind of overarching picture. And so next week, we will continue a little bit with the discussions on how to build codes. We are going to show you how you can use TensorFlow, which is a popular library for machine learning. But we're also going to postpone the discussion of automatic differentiation till next week. So I had some idea of doing it last week, but we are going to postpone automatic differentiation to next week in connection with the solution of differential equations, because then you will see how you can use the codes which we have developed to specific applications. And then you will also see why it is convenient to use automatic differentiation. In project number 2, we're actually asking you to hard code the derivatives, simply because that gives you more control. And the functions which you're going to study, both the loss function and the activation functions, are pretty simple. So it doesn't take so much time to actually find the derivatives and then just hard code them. And this is also something which strikes a balance between the number of floating point operations and the development time. Because when you use automatic differentiation, that takes always some more floating point operations than you having hard-coded the derivatives. And the activation functions we are going to study are pretty simple ones. But when you move into a regime where you're going to apply many different types of activation functions, then it's convenient to actually use automatic differentiation, because then you would like to strike a balance between development time and runtime. So the total time of a project is not only runtime, it's also your development time. And that can be a huge fraction of time. Okay, so one thing I want to do now in the next few minutes is to repeat a little bit of the things which we did last week. And then I want to set up the final equations for the back propagation algorithm, so that you see all the equations which are going to be coded in the exercises this week and in the project. So let's take a look at what we did last week. So it's a repetition of roughly 10 minutes. I hope you don't mind that. So let me just bring that up and remind ourselves a little bit about what we did last week. And what I'm going to do then is to bring up the slides again with the simple examples which we looked at. So let's just enter full screen. So what we did was to take what we called a simple perceptron model. We had a scalar in and a scalar out, and we had only one scalar parameter. And the model which we had then was a model which now took an input variable x. There's only one variable. In the exercises you had last week, you actually looked at cases where the x here was replaced by a vector or a matrix, which is the more common case. Then we had the weights and the biases. So W1 and B1 are the unknown parameters we want to optimize. This Z1 is then the argument to this activation function. Now, in project number 2, when you're doing a regression case, the output layer is then going to have as output only the function value. It's not going to be modulated by anything. So it's a typical situation when you deal with a regression case that the output layer doesn't have an activation function. Now, for this simple model, we looked at the mean squared error. The A1 is the output of the model, and the graphical representation is the one you see here. So you have an input, the unknown parameters, this gets modulated. So this is called the simple perceptron model. There is no hidden layer. And that means that the first layer is also the output layer. And then it produces an output which feeds into the cost function and is then compared with your target value. And the way we find these parameters is again by optimizing the cost function with respect to W and B. That's essentially what we did last time. And then what we needed is these two derivatives. And when we applied the chain rule, what we found then is that since, if we now look back here, C depends on W1, but then the output is A1 through this function sigma, And this output comes in here. So when we take the derivative with respect to W1 or B1, then we have to use the chain rule to get to the expression which you see here. And the basic structure which you have in this simple scalar model, one variable in, one variable out, is a model which then essentially has the essential elements of a neural network. And except that here, we are not looking at vectors and matrices, which represent more complicated data. And one of the things which we did was to represent a function which we label as delta 1, which now is this set of derivatives where a dA1, dZ1 is nothing but the derivatives of that activation function. And when we did that, we modified this to add two layers, one layer. So we had a hidden layer here. No, sorry, a hidden layer here. That produces an output, which now is fed into the output layer. And that produces a final output, A2, which goes into the cost function. And then we have to propagate back to find all the derivatives. So then we took the derivative with respect to W1, W2, B1, and B2. And when we did that last time, we ended up with a little bit more complicated expressions. So we brought together these two terms here into a delta 2. When we take the derivative with respect to B, because B is a little bit simpler, the B dependence, because you see now that when you take the derivative of Z with respect to B, that is just 1 here. Now, we did include this bias because we want to have a possibility that in case the W's are initialized to 0, which could happen if we initialize them randomly, then this bias is starts with a small value, non-zero value. And that is simply because the training of the network stops if one of these parameters is 0. And we want to avoid that. Then we could then retrace back and we get all its derivatives through the chain rule. And it's essentially a neural network since we are going to deal with vectors and matrices, which represents the input and the outputs. Then we are going to have a chain of derivatives through the chain rule. This is essentially what we end up doing with a neural network. And what I'm going to do after this is to set up the equations for the back propagation, and then we have the expressions for the final gradients. And so what you see now is that the derivatives of the activation functions play a central role. If they vanish, then the training may stop, and that's called the vanishing gradient problem. And if you go into the slides, you will find a discussion today about this topic here. And if they become large, then the parameters W1 and Wi and Bi can simply go to infinity. And that's also the problem of exploding gradients. Now, there are many ad hoc tricks here, and one is just called, believe it or not, gradient clipping. So that means that if the gradient becomes too large, you reset it to a smaller value, and then you keep the training. So, because in many cases you have so many variables that you cannot control all of them. So gradient clipping, in case the gradient becomes too large, is one of the common techniques which is used to avoid that the training just dies out or that gradients explodes. So just keep in mind now that every loop forward and back updates your parameters once, and then you go back and forth till your cost function doesn't change by a prefixed amount. That could be the mean square error, which is one of the functions you are looking at as a way to gauge the quality of your training. Or if you're doing a classification problem, it could be the accuracy of your model, where you simply count the number of correctly classified events. That's a pretty simple one. You just count the number of correctly classified and divide by the total case number of events. Okay, so the typical problem you end up with when you have these derivatives, and now we are going to set up the general expression for this delta y, and is that we have the output from the previous layer, multiplied with this parameter, which contains several derivatives, times the learning rate, and then we have the previous value here. And this are the equations which you get for every layer and every node. So the subscript I here, is a node in a given layer. And when you have many nodes, typically 50 to 100, which is not uncommon, then you have lots of parameters in every layer. And we call this deep learning simply because the more layers you have, the deeper the network. And that's where the name deep learning comes from. So let me ask you one thing, which is relevant for project number 2 here. So if you look back at the project 1, when you fitted a polynomial, your design matrix reflected the order of the polynomial. When you now do a neural network, should the input matrix or the design matrix be the same as when you did fit a polynomial or not? So just give it a little bit time, and then there's a question, yes or no. So the answer is just yes or no. So if you say yes, then you raise your hand. If you say no, you don't do anything. Okay? I didn't prepare the quiz online today. So think of this. So in project 1, you set up a design matrix which reflected the order of the polynomial. So if you had a 14-folder polynomial, you had 15 columns in the design matrix. You would have the intercept column, x to the power of 1, x to the power of 2, till x to the power of 14. That was your design matrix, because then you fed in a polynomial order. When you do a neural network, does it make sense to feed in the same design matrix or not? So who thinks yes? Really against that? I agree with you. The reason for that is that now the neural network is going to find the best model for you, the best representation of the function. So that means that you feed only the x values. Because if you feed in a polynomial to degree 14 to a neural network, the neural network will try to reproduce a polynomial of degree 14. And your function may not be described by a polynomial of degree 14. It could be a polynomial of degree 100. So the network, by its architecture, is supposed to find the best model for you. So feeding in something like you did in project 1 doesn't make sense. Or rather, you can do it, but then you're not exploiting the properties of the universal approximation theorem. Because that says that given at least one hidden layer, it's going to find the best representation of your function with a given error. That makes sense? So just keep that in mind, because it's easy to make that error in project number 2 when you're comparing the results from project number 1 with what the neural network gives you. It's good to see that most of you reacted with a no here. That's good. Okay, so what I'm going to do now is to go back to the whiteboard, and we are going to remind ourselves of the equations, which we almost finished last week. So we're going to set up the final equations for a neural network, and then we are going to discuss how we can encode this. So I will show you the different elements of a program which sets up a basic neural network with one hidden layer. Okay, so let's switch a little bit back to the whiteboard, and let's try to finish what we did not finish last time. So where we were last time was we had almost done the last step, and we had a layer. So I'm just going to write it like this, and this was layer L minus 1. And then we had a layer L like this. So this is a given hidden layer. And then we had a set of nodes here, all down here, and all the way down here. And these can be different, but it's pretty common that if you have a dense layer, you have often the same number of nodes in the central layers, and then you can have some less at the end. Then what we looked at was the connection between these and a specific node here, and we called that specific node that got an input which we called for set J in layer L. Now this receives input from all nodes here. This is the standard setup for a neural network. Now there are ways, hard-coded ways to reduce the connectivity. And there's something which is called dropout, where you can decide whether a node feeds into the next one or not. And that's a way to reduce the dimensionality of the weights you're training. So what happens then is that we have an output here. So this will be an output A1 from layer 1 here of layer L minus 1. There is an output A2 from layer L minus 1. And these all feed into this node, but they also feed into the other nodes. Then there is a weight which connects this one, W, and we call this for W1J of L. And this function's Zj of L was then given by a sum over all the nodes which you had in the previous layer of NL minus 1. And then we have the weights, Wij of L. And then this is multiplied with the output from this layer, L minus 1, plus a bias of Bj of L. So that was the input, a specific node. Now that node, again, produces an output. So last time, we then defined this output, Aj of L, as a function, as a result of the activation function receiving this input and then producing an output. So sigma is the so-called activation function. This is a quantity you will play around with in project number 2 here by using 3 different types. We are going to use the sigmoid or logic function, and then we are going to have 2 popular ones which are also used. One is called the ReLU and the other one is the ELO function. And we are coming back to these properties a little bit later. So these were some of the quantities which we defined. And then we have a cost function. When L is equal to L, then we have the final output, Aj of L, and that feeds into the cost function. And so the cost function will then receive these variables. It compares that with the target values. And then we have a set of parameters, theta. And theta are the parameters we want to optimize. So what we want is obviously to set up. So let's just also write, if we have the mean squared error, to give you an example. And this is the first encounter in project number 2. And I'm just writing this as a C of theta. This would be something which we would typically write as a sum over all the variables we have of n, and then we have an Aj of L minus Yj squared. And then we would calculate dc d theta and have that one to 0. So that's ideally what we want. And let me quickly remind you of some of the intermediate result which we had, which we needed. So we looked at one of these quantities with respect to Wij in a layer L, and then we're going to put L equal to the uppercase L. But this is a quantity which is just given by AL minus 1. And you will see that when you go back to this expression which you have here, and you take the derivative with respect to Wij, and then we get this expression here. That was one of the intermediate steps we needed. Then what we also did last time was to set up another intermediate step. So let me see if I can move on here. We had DC, that these are just intermediate steps which we need to find the final expressions. And then we have a DAI of L minus 1. And this is the same as WIJ of L. And then we also found that DAJ of L with respect to DC of J of L for layer L, that is the same if we use the sigmoid function. If you have other ones, you need to set in other expressions, sigmoid for sigma. Then what we got was an AJ of L of 1 minus AJ of L. So that's the sigmoid function if we have that as an activation function. If you have other ones, you need to find them. And this is one of the quantities you need to hard code in project number 2. And it's very common that for all the hidden layers, you just run with the same activation function. The only thing which changes is the output layer. And one of the cases which we're going to look at is this MNIST data set in project number 2, where you're going to have 10 handwritten numbers. So that means that you would have 10 output nodes with a probability for each number from 0 to 9. If you're looking at the function value, then this is just the final value without any activation function. So that means that it would just be in the output layer, it would just be the variable Z as an output from your network if you're fitting a function. So just keep that in mind that you have different cases depending on what kind of problems you're looking at. So what we did then is that you start with L equal to the final layer. This is the final output layer. And what we have then is a C of theta, which is given by, if we now are looking at the mean squared error, and I'm just putting this as a sum over I without specifying the end. So this is layer L minus Y of I, which is the target value. This is the one we want to reproduce. Then what we found last time is that, and I'm just going to set up the result because I'm not going to repeat all the calculations, is that this D of C of DWK for layer L, the final output layer, is then given by, in this case, a variable JL, the output from the output layer, YJ. And that is a quantity which comes from the specific cost function. If you have the binary cross entropy, which we will have for classification problems, this function is going to be different. Then what we have is a new function which goes like AJ of L times 1 minus AJ of L. And this is the derivative of the cost of the activation function in layer L. This is also specific for the activation function you're looking at. If you have another activation function, you need to plug in another derivative. And this is finally multiplied with the input from layer L minus 1 from node K. And then it's pretty common, as we said last time, to collect these variables. So this quantity which you see here, just to remind you of that, this quantity is DC DAJ of L. This quantity which we had here is then simply the derivative of the activation function, which we just wrote like this at the output layer. Now, what we did last time was to bring together this one and that one into one variable. So when we did that last time, so let me do that, that gave us a new variable, which we call delta J of L, which was simply given by the derivative of the cost function with the output from the last layer multiplied with the derivative of the activation function. So that meant that we could write dc of dwjk of L in terms of a delta J of L times this AK of L minus 1. So that's the output layer, okay? And then the other thing which we found is that this dc of D of dj of the final layer, the bias on the final layer, that is equal to dj of L. So these are the equations for the derivatives in the output layer. So we can frame them in, because that allows us to set up the gradients and then do the update of the parameters. So let's just write that down. Let's just wait a little bit so people have time to write down. Okay, so let me just move on. So what we would have then is that these parameters, and I'm just going to write it with a parameter jk in layer L, they're being updated with a previous value minus, and then I have a learning rate, and this is where our gradient method comes in. And then I have this parameter delta J of L of AK from layer L minus 1. So this is not a plus, it's actually a minus L minus 1. And then I have a similar one for the B's, which are then being updated by Bj of L minus eta of delta J of L. And I have these expressions. Now, what we need next is actually these derivatives at a random or a given hidden layer. So what we are going to do next now is simply to let L go to a given layer L. And that will give us the general algorithm for updating the parameters. Okay? So what we are going to do then is that we need some of these help expressions. So we have this delta J of L. This is something which we showed last time, can be written as a dc, the cost function, but now as a derivative at layer L. Now I can now use the chain rule and rewrite that as a sum over all the derivatives from the previous layer. So this is now going to be given by, if we use a chain rule, of dck of L plus 1, and then I have a dck of L plus 1 with respect to the value at node J in layer L. So what you can think of now is that L plus 1 is equal to your output layer. Then I step in to the first hidden layer from the output layer, and that is L. And then you step backward till you reach the final input layer, the hidden layer right after the input. So what I'm going to do now is simply to use the chain rule. And the thing is that this quantity which you see here, this is nothing but, so let's just wring that out. This is nothing but delta of K for layer L plus 1. So if L plus 1 is the output, then we have found it from our previous calculation, because then we have the variable here. So this is the same quantity. So the reason why I'm writing it like this is simply because if you now look back at the expressions we started with, when we take the chain rule and set up this expression, what you end up with is that that quantity which you see here is simply dc with respect to because this quantity you see here, this one, let me just ring that one out. That is the same as dAj of L of dCj of L. So when you see that expression here, if you take away this one in the expression, you simply have dC with respect to that quantity, and that's the one which I used here. Then I go down here and I have that expression, which I know because I started at the output layer. And then what I need to find now is actually what this guy looks like. And if I find that one, then I have the final expressions for the backpropagation algorithm. So what I'm going to need then is simply remind myself about some of the definitions, because I have that Cj of L plus 1 is now simply given by the sum over I equal 1 over all the nodes in the previous layer multiplied with Wj of L plus 1 and multiplied with the output L from that node plus the bias of L plus 1. And then I know that this Ai of L is nothing but the output of Ci of L, like that. So that means that this dCk of L plus 1, which I had in that expression on the previous slide, has simply to be given by Wkj, if I look at that one, of L plus 1, multiplied with the derivative of the cost function with respect to the input to node j in layer L. So when I then have that, then I can find the final expression. So I have a delta j of L, which is then simply given by, and this is the final expression we need, by a delta k of L plus 1. So we have pre-calculated that one. We need to keep track of these weights of L plus 1. And then we have a derivative of Cj of L. And that's the final expression which we need in order to set up all the gradients. This is the final expression for the backpropagation algorithm, where the thing we have done is simply to use the chain rule, starting from the output layer and going back till the first hidden layer. So with these expressions, what you can do then is simply to set up the updates of gradients and these updates now contain a Wjk of L, which is then given by the previous value of L minus this learning rate, which is a parameter we have to play around with because we don't want to calculate the second derivative of the cost function. That's going to be a nightmare. And then we have an AK of L minus 1. And then we have a Bj of L. That's the other parameter in a given layer. Bj of L minus eta times delta. No, sorry. The derivative of C with respect to Bj in layer L. And this quantity is nothing but delta J of L. So the backpropagation method gives us these deltas. Then we have the expression for the gradients, and then we can do the gradient upgrade. Oh, no, sorry, not the gradient upgrade. The upgrade of the parameters by calculating the gradients, and then we update the parameters. So this is the same expression which you coded in project number 1. And that's where we need the stochastic gradient descent or the gradient descent to update these. But we need to do it for every single layer and every node in every layer. So If you then have 1 million such parameters, you need 1 million such updates. And these equations here are then given by effectively matrix vector and matrix multiplications. That's essentially what we end up with setting up. Because we will rewrite this equation here as a matrix which contains the parameters. And this is going to be a vector, and this is also going to be a vector. Okay? So what we will do pretty soon now, after we have summarized this and set up the algorithm, is actually look at how we can implement it. Okay? So these are the expressions. This is the backpropagation algorithm, which is nothing but you applying the chain rule again and again. So the algorithm for a neural network, when we are setting that up, is going to look at as follows. And after the break, we are going to start writing a code which implements this algorithm. So the first thing is that you need to define the architecture. So you need to define the architecture, and keep in mind now that the architecture of the network is your model. So I'm just going to write in parentheses here, the model. So this means that you need to define the number of nodes, the number of hidden layers, and then you need also to define the activation functions. And you need obviously to define the cost function. So when you've done that, then you have defined these parameters. Then we need to initialize the parameters. Initialize theta, which is now a collective container for all the weights and all the biases. So as I said, if you have 50 input nodes and one hidden layer with 100 nodes, then the dimensionality of the weights is going to be 50 times 100. So you're going to have 5,000 weights. And then since you have 100 nodes, you're going to have 100 biases. So in total, then you will have 5,000 plus 100 parameters, 5,100. With just one hidden layer, 50 input nodes, and 100 hidden layer nodes. So that's the number of parameters. And then you're going to have an output layer which connects with the hidden layer. And we are going to look at that after the break, and we're going to do the counting of the number of parameters which we are going to get. Okay, so we initialize these parameters, and this is typically done by random variables, which are small random variables. We need to set up the design matrix. So set up design matrix. So if I have a two-dimensional function I want to fit, so that means there are going to be x and y values. And suppose I have 100 input variables for x and y. What's the dimension of the design matrix if I run a neural network calculation? How many columns do I have if I have a two-dimensional object? Say it again. 2, exactly. So you have one for x and one for y. And if you have 100 values of x and y, then you have 100 times 2-dimensional matrix. Clearly, your output then, since you have 100 variables x and y, for every x and y, there is an output value. So there would then be 100 output values. just to give you an example. So that's how you would set up your design matrix. So let me just quickly set up this, and then we take a small break. So what you also need to define is to set up the learning rate. Eventual hyperparameters. You need to define the gradient methods. So these become all parameters which you will experiment with. And when you have defined that, that is your final model which you will train with a specific gradient descent method using, let's say, Adam to update the learning rate. Then the first thing you do then, one, you perform a feed-forward pass. First, feed-forward, FF, step, and continue. So you do that from hidden layer, L equal 1 to L equal the final output layer. And that produces A of L. And I leave that as a vector now, because you may have, let's say, 10 nodes. So that would be a vector with 10 elements. When you've done that, then you do the back propagation part. So what you would do when you have this is that you compute this delta JL. And then the next step, then back propagate. And now we're going to stop. So we can take a small break, but let me just write it down so we are ready to design our code after the break. So we do this for L minus 1, L equal to L minus 2, and we go down all the way down to the first hidden layer. And for each one of them, we compute this parameter delta JL for each one of them. And then we train gradients. Train gradients so that we can update. And then we update WJK of L, which is given by the previous value, minus eta times this delta JL. And in this case, this is multiplied with an AK of L minus 1. And then we have BJ of L, which is being trained by the standard formula, which we have seen many times now, times delta JL. And then we continue till convergence. And this can typically be, if you're looking at the mean squared error as your measure, then it could be till the mean squared error doesn't change by a prescribed amount, which you have defined. So every step, one feed forward and one back propagation gives one update of the parameters. And you can think of that as one iteration. And then you go back and forth according to how many iterations you're willing to do. And then you would stop. This is the training via a neural network, using the back propagation, which gives you the expression for the gradients. Does that sound okay? So after the break, we are going to look at how we can implement this. And we are going to look at a case which is pretty close to project number 2, which is the MNIST dataset. But I'm going to look at a downscaled MNIST dataset, because that's going to be pretty fast in the lectures, whereas you will look at the real MNIST dataset. Okay, I went deliberately a little bit over time because I just wanted to set up this final step so that we have all equations and the algorithm in front of us when we begin next lecture. Okay, I'm going to put on pause here. So let me quickly remind you about what we have developed. And then we are going to dive into the structures of the codes. We are first going to look at a simpler case, and then we will jump into the programming of the MNIST dataset, which is a dataset which we are going to have as a dataset in project number 2 as well. However, keep in mind that you can always replace the dataset which we suggest with datasets which you think are more relevant for your research. So we don't get offended if you do that, please. So, because I mean, we just set up a data set which has been studied a lot, which makes it easy for you to compare with what has been done by other people. And we also wanted to have a simple regression case where you can compare neural networks with what you did in project number 1. And then that allows you to also hopefully gain some insights about the pros and cons of a neural network towards a much simpler approximation method like ordinary least squares. And sometimes if ordinary least squares does a better job than a neural network, there is no point in hunting after sparrows with big artillery, right? So the neural network is a very powerful method, but if you have something extremely simple, then probably ordinary least squares does a better job. And then the other case we're looking at is a classification problem. And the classification problem which we are going to deal with is a multi-class classification problem with 10 handwritten numbers from 0 to 9, where you have 60,000 images, which you then are going to use in the training and then make predictions on a subset, which is the test data. That's essentially the main task in project number 2 when you have developed your neural network code. So as I said, you define the architecture, and that is your model. So that means you define the number of nodes, the hidden layers, the activation functions, the cost function, and you have a design matrix which reflects the input data. You fix the learning rate and the hyperparameters and the gradient methods. And then you run. And then you can change the gradient methods, you can change the number of nodes, you can change the number of hidden layers, and that's a new experiment. So typically what is done when you run a neural network is that you don't know before you've run the calculation what you will get. So that means that you have to run many experiments. And that's the standard situation. And the first step is the feed forward, and you continue then till the last layer. When you're at the last layer, you have produced an output. With the output, you compute these derivatives of the cost function at the end layer, and then you back propagate with a formula for the updates of the derivatives given by the chain rule. And when you have the expression for the derivatives, you can then use the standard gradient descent schemes to update the parameters W and the parameters B for every node in every layer. And that's a tedious part. So if you look at, let's say, large language models, these can have trillions of parameters. So in the calculations which we are going to run, we are going to be in the tens of thousands of parameters. And the case I'm going to show you now is a much simpler case. And it's a scaled down version of the MNIST dataset. So the original dataset has something like 60,000 images of handwritten numbers between 0 and 9. The scaled down one, instead of 28 times 28 pixels, has 8 times 8 pixels. So every pixel defines an input node. So in this case, it's going to be 8 times 8, 64. And I'm going to have 2,000 images. So I'm going to have 64 input nodes per image. And then I'm going to train 2,000 images on that. So that's the definition of my design matrix. 6,000 input data, and then each input data has 64 pixels, 64 nodes. If you're fitting a function in one dimension, like the one you had in project one, you can have 1,000 input variables, and that means that for every x, there is an output y. So that means that you have, for each x, there's only one output. So that means 1,000 inputs, you train on 1,000 data points. So as soon as you have pictures, you see quickly that the dimensionality can explode. And that's why in 2 weeks, we are going to encounter convolutional neural networks, which is the next method, which is a much better way of scaling down images. Because if you have an image, you may not be interested in keeping all the information in an image. So if you want to recognize houses, you're not interested in the color of the house, but you're interested in where the corners are, where the roof is, where the windows are, where a balcony is, and where the door is. And you would only keep that information. So you would filter down the information to a smaller image, which then keeps track of a specific type of information. And then you would train on many images of houses, and then you would have a model which recognizes whether this is a house or not. But now we are going to just do in project 2 everything in a brute force way. So we're going to feed in the whole image, which means again that we will get lots of parameters to train, and the matrices will be dense for the weights, the unknown parameters, and we call this affine transformations. So we're going to have a matrix which represents the weights multiplied with a vector which represents the inputs or a matrix, and then this is going to be propagated through the network. So the exercises this week and the previous week deal with exactly this. Okay, so I'm going to go back to the Jupyter notebook now, and let's do that. So essentially, the situation which we are going to deal with is something like the one you see in the image here. And you will have a set of input nodes. If I have a classification problem with 3 classes, I will have 3 output nodes. So this could be output type 1, output type 2, and output type 3. We are going to have now 10 types of images, the handwritten numbers from 0 to 9. So we will have 10 output categories, and there will be 10 output nodes. So if you now look at the different, so this is essentially what we went through here. So as I said, if we now look at the way we are going to set up, so we need to set up your inputs and outputs. These can be scalars, vectors, matrices, or higher order arrays, tensors. Define the number of hidden layers and hidden nodes. You define the activation functions for hidden layers and output layers. If you're fitting a function, there is only one output, the function value, and then normally you don't have an activation function for the output layer. You need to define the optimizer, which you want to implement. And we are going essentially to try root mean square propagation and Adam in project 2. We are going to define the cost function, regularization terms, initialize weights and biases, and fix the number of iterations for the feed forward and the back propagation part. So the equations which you saw before the break, they are summarized here. I'm not going to repeat them, but essentially you have the equations here, which we derived before the break. So we need to set up for the output layer. We have for any hidden layer, we have a layer L here. And then when we set up the algorithm for the derivatives, we have the gradients. And then we can update the parameters as we discussed. And then we keep updating the gradients. And this is the final formula which we need to plug in. So where we have the outputs from a given node, and then this should actually be L plus 1. That's L plus 1 here. Sorry. That's a typo. I have to take a note of that one. It's correct in the code, actually. Let me just correct that one. So there are some things which we are coming back to now, and that is about the activation functions. So when you look at the universal approximation theorem, there are some constraints on the type of activation functions. We want them to be continuous, or they can be discontinuous at a certain point, bounded and monotonically increasing for the area which we're looking at. And some of the more typical ones which people use is the sigmoid and also the tan X. And you will typically see that if you plot these functions, and these are some of the functions you're going to use in the project. So you have a sigmoid here, and this is the one which causes problems when the values of Z become very large, because then this function is going to be flat, and that means that its derivative is going to approach zero, and that causes problem with the training, because if the derivative is zero, that means that the gradient can become zero when we are training the network. And that was the problem which I mentioned, which is called the problem of vanishing gradients. And that was also one of the main reasons for why neural networks actually never took off before roughly around 2008, 2010, when Ben Zhou and other people actually pointed out the problem with the sigmoid activation function. And then people have been playing around with other activation functions, like the step function is not recommended because it is discontinuous. And discontinuities are something which often create problems when we are dealing with it numerically. We obviously have a sine function. There's another function which is very much used, which is called the rectified linear unit. So this has a discontinuity at zero. It's monotonically increasing. And then the problem with this one is obviously that it is zero below a certain value. And then people have defined something which is called, so this is called the ReLU function, rectified linear unit. And it's a very popular activation function because you see that the derivative of that one is easy to calculate. So think back to the equations you're dealing with. When you're updating 1 million parameters, and these 1 million parameters depend on the derivatives of the activation functions, then you want something which is simple to calculate. We don't know which is the best activation function, and that's why people try different activation functions for different types of problems. And if you search online, you will find at least 10 to 15 which are very popular. There are Gaussian type of functions. There is an exponential type of this leaky unit functions. And one of the functions which has been very popular and is simple to use is called the leaky ReLU function. So that means that the leaky ReLU has actually a small value here. It's a straight line. So it's non-zero when Z is less than zero. But it takes just a small value. So it leaks values from zero. That's why it's called a leaky ReLU. So ReLU is a rectified linear unit. That's what it stands for. So you may be surprised when you look at these functions because some of them may not be directly linked with the kind of science you're looking at. So I've often been studying quantum mechanical problems, and then I try to use activation functions which mimic a quantum mechanical wave function. So if it's a harmonic oscillator, which looks like a Gaussian, I often use Gaussian activation functions. And these are called GLU. So Gaussian ELU function. ELU stands for exponential. So all of these functions have parameters. And these parameters become parts of your model. Because the way this function rises has obviously a slope. And that slope is a parameter in front of the value of Z. And you will see that in all these activation functions, which we're going to play around with, the way they are implemented in the codes, you will see that there are different types of activation functions. Actually, at the very end, so let me just anticipate something. This is something which comes at the very end of the notes here. And you will find a object-oriented code here, where we now have implemented the different methods which you did in project 1. And you recognize here the different method Adam root mean square propagation. But then you will also find cost functions. These are the cost functions we want you to plug in. But you will also find a set of activation functions. And here you will find typical functions like the sigmoid, the softmax, which is used for multi-class functions, the rectified linear unit, and this returns simply as a value when x is larger than 0. We have this leaky ReLU, and you see now that there is a parameter. Now, these functions which you see here are the functions which we are going to use in the project and as activation functions. And then we need also their derivatives. And here you will see that we have calculated the derivatives analytically. So this is just to anticipate something which you need to encode in project number 2. Now, if you have many activation functions and you want to play around with many, then it's pretty common to replace the hard-coded derivatives with automatic differentiation. But still you need to give some expression. So these functions which you see here are typical activation functions, and they become parameters of your model. And then when you fixed one of these, that is your setup, and that is your numerical experiment. Does that make sense? You're not fully convinced here. So you have to view a neural network as you setting up parameters for a numerical experiment. And where the guiding line is the universal approximation theorem. So let's go back. And what we are going to look at now is the setup of a, in the slides here, you will find some discussions which we are coming back to on how you can fine-tune parameters and so on. Concerning project number 2, the parameters which the results are most sensitive to is the learning rate and the hyperparameter lambda, which is the same as you had in lasso and ridge regression. So what is pretty common when you run these calculations is that you try to find or fine-tune lambda and the learning rate, and then you can play around with the other parameters like the number of nodes, number of hidden layers, etc., etc. So these are often the parameters which the results are most sensitive to. But we are now going to look at this MNIST data set. So let me just do that before we discuss more these kind of technicalities here. There's one thing with the data set which we have. So we are dealing with what is normally called a discriminative method, because we are going to feed in, let's say, images, and the model we will train will then allow us to discriminate between the different images we feed in, whether this is number 0, number 1, 2, etc. And the data which we're feeding in is a homogeneous set of data, and it's also labeled. So that means somebody has labeled the data for us. And this is a typical limitation of many of the problems which we deal with, because many problems in science are not about predictions. And sometimes we're often interested in learning something about the underlying distribution that generates the data. But let's now try to set up a neural network. So we are going to set up a multi-layer perceptron model or feed-forward neural network. These are synonymous for classification. And we are going to develop an example which is based on this MNIST dataset. NIST stands for the National Institute of Standards. And this dataset originally consists of 60,000 images. This is the one you will use in the project. But in the lectures here, we're going to have a downscaled 1-1. So in a binary classification problem, you would typically have 2 classes, and then the output would be 0 and 1, typically. And then you would have a probability distribution for y equals 0, which could be the sigmoid function, and y equal 1, which is simply 1 minus this one. And these 2 probabilities sum to 1. So when you deal with a cost function, and this is the typical cost function which you will have for the binary case, which we will not study in project 2, but you're going to write a code where you will have this one as well, so that you can actually use your code for a binary classification case as well, if you want to. So we want you to develop a flexible code which allows you to look at a binary classification problem, a regression problem where you fit a function, or a multi-class classification problem. So these are the 3 cases we want you to look at when you write the code, but the data which we're going to specialize on is a multi-class case and a regression type of problem. And there's a reason for that, simply because we don't want to overload you guys with too many data sets to look at. But again, feel free, if you want to study a binary class problem, you can replace the data set which we have suggested. Okay. So this is the cost function which we're going to set up. And in typically this type of multi-class problems, it's actually common to treat each integer label, like here y equal 5, could then be translated into what's normally called a one-hot vector. I prefer to call it a bit string. This is just a naming which you will find in the literature. So you would typically replace a given handwritten number which is labeled with a specific coding here, like a bit string. So if you have 10 handwritten numbers, you need 10 bits. And the case which we are going to look at is the numbers from 0 to 9. Then the probability is then going to be given by you having one of the classes where this could be number 9 or number 0. And then this is called the softmax function, and it's an extended sigmoid function. It plays the same role as a sigmoid function, and all these probabilities sum up to 1. I'm coming back to that one when we discuss this more explicitly in the lab sessions. Now I just wanted to set up the equations. So this will be the number of data points which you have, and then you have the different classes. And if you take the negative log, this is the function you want to optimize. If you have a binary classification problem, these are the probabilities you can have. When we discuss logistic regression, this was a type of the functions which we would fit. So we can have more than just one feature, but we could then, if we have one feature here, we have parameters beta 0 and beta 1. And this would be the parameters which we would fit. And then when we take the derivatives, we end up with the equations for logistic regression, if that is the case we want to look at, or we can do a neural network. If we do the softmax function, what we end up with is an output from each node, which is then given by this function here. And then the inputs, this is still the binary case. Let me just scroll down a little bit here. This is the derivative at the output layer, which is now different from the one which you had for the mean squared error. For the mean squared error, what we had was this quantity here, this one, without this quantity in the denominator. This is because we are now taking the derivative of that function. So this would be the derivative of the cost function at the output layer with respect to the output parameters. If you take the softmax function, what you will have to do then is simply to calculate these derivatives, and then you need the derivative of the activation function, which then is now given by this function here. And this is something which we will leave. This is actually one of the exercises in the project, which we want you to look at. But you have the answers here. And we want you to go through these derivatives in the project. So when you're setting it up, what you want to do is then collect and pre-process the data. You define a model in the architecture. You choose the cost function and optimizer. You train the model. You evaluate the model performance on the test data. And then you eventually adjust hyperparameters. And now I want to go through the elements of setting up a neural network code with one hidden layer. So we are going to use the MNIST data, which you can get through the scikit-learn library. The data set has 70,000 images, and this is the dimensionality. But here we are scaling it down to roughly 1800. And then we have 8 times 8 pixels. So each image is pretty blurred out. So let me just skip this one, but let's now look at how we would read it. So the data set is called low digits. In the project, there is an example. So scikit-learn does not contain the big data set. But in the project, there is a description on how you can access the full data set and then use scikit-learn functions like train, test, split, etc. Okay? But now in the lecture here, I'm just going to run through the scaled down version of it. So in this specific case, the function which we need to call is the function which is called low digits, and that gives us the data set. And when you now look at it, some of these numbers are pretty blurred, as you can see. And I actually have to confess I have problems in identifying this as a number 8. Some of the other ones I can buy, but many of the other numbers are actually really downscaled. And unless you have a label on them, I would say it will be difficult for me to say that the one to the left is a number 8. But this is a downscale number 8. If you look at the full data set, you will see that it looks like a number 8. But these are handwritten numbers, okay? So this is a data set we are going to train. And then you can see that if we do the standard, we do the standard 80% for training and 20% for test. And in that case, you see now that this is the data set we are setting up, 1400 and 360 for testing. And then you need to define the architecture. And we are going to look at the input layer, which now has 8 times 8 equal to 64 pixels. So these are the features. We need to set up the hidden layers. And in the network here, there are 50 neurons in the hidden layer. And they receive an input from the neurons in the input layer. So when you now are looking at the exercises for this week and the previous week, this is essentially more or less what you did in some of the exercises when you set up the network and the number of hidden layers, etc. So in this case, you have 3,200 weights from the input layer to the hidden layer. So this is the number of parameters. So if you then have an output layer, so the code which you will see here is just a code with one hidden layer only, okay? And it's written in a way which is a little bit, how to say, less flexible, because ideally what you are going to do in the project is to write a code which is more flexible so that you can add or decide how many hidden layers you want to have. So the way I've written it now is a little bit static, but the first code here is mostly meant as a way to demonstrate the backpropagation algorithm. So if we now look at this handwritten numbers, we are going to have 10 categories, and then we would typically use 10 neurons or 10 nodes, as we call them, in the output layer. And then we will have the softmax function to give a probability to the given type of output. So each neuron J outputs a probability of being in a class J, given an input from the hidden layer. And this input is A, and with a weight WJ. So in this specific case, we are going to have 50 inputs from the hidden layer to 10 nodes in the output layer. And that means that we have new 500 weights. So we have 50 nodes in the hidden layer, which means that we have 3,200 weights, which connect the input layer. But then we also have 50 weights for every node. And in the output layer, we are going to have 10 additional nodes. So when we collect everything here, you see now that we are going to set up the number of hidden neurons, 50, the number of categories, 10. And then we are initializing the hidden weights by some random number. And we are given, so some of these could accidentally, so these are random, normally distributed numbers. We would then we could initialize some of them to be 0. And that's why we put this bias to 0.01 here. So this, what we're doing here is simply to set up the inputs, the number of inputs, the number of features, and that's given by the training data here, which we have. We did define hidden neurons. That's going to set up the dimensionality of the weights. And you can see that that's given by the number of features, the 64 pixels. And then we have hidden neurons, which are 50. And we do the same thing for the outputs. So we have the hidden neurons, which then connect to 10 categories, 10 classes. So this would be then a matrix of dimension 50 times 10. And this is a matrix, as you can see back here, of dimensionality. Let's see what I have it, 64 times 50. And then I'm doing a feed-forward pass. So these are the parameters which we discussed before the break. I have my activation functions, these A's. I have the hidden layer and the output layer. This is the hidden layer, and this is the output layer. And this is the output from the output layer. You see this parameter L, uppercase L. This is my output layer. And then this is now given by the softmax function, whereas the hidden layer uses the sigmoid function. And then I'm doing a matrix multiplication, where I take my feature matrix, X, which contains my input variables. So if I have 1,000 images and 64 pixels, this matrix X is 1,000 times 64. This is a matrix which contains all the weights. So that becomes a matrix of dimensionality inputs times the number of hidden. Then I'm setting up Z here, which then is simply given by this matrix multiplication plus the hidden biases. This gives me now a variable Z, which can be a vector. It feeds in here. It produces an output, which then is plugged into the output layer. And then I have the output here from the layer, which I want, and then multiplied with WL plus the biases. So in the code here, I've set up the feed-forward pass. I have the sigmoid function. So my feed-forward pass has a variable C for the hidden inputs to the nodes, to the hidden nodes. And that is given by a matrix multiplication of the input matrix times the weights, obviously. So this is a matrix multiplication, hidden weights times X plus the hidden bias. And then I have the activation in the hidden layer, which is given by my sigmoid. And then I have the weighted sum of inputs to the output layer, which then is now given by a multiplication of the output from the hidden layer and multiplied with the weights of the output layer plus the bias here. And then I have a output, which is now given by the probability, this C0, and then divided by the sum. So this is nothing but the activation function for the softmax function. And that returns as probabilities. And the probabilities is then given by the feed-forward multiplied with this X train here. And then if I do that, then you can see now that the prediction for my image, this is the feed-forward pass. So I had a label for this image 0, which was number 8. But I make a prediction to be number 8, but the correct label should have been 6. So this is my feed-forward pass. Now I need to set up the training of the network. So let's try to do that. So I'm going to skip not all the details here. So I'm going to set up my gradient descent. And this is essentially the same formula which we have been discussing again and again. I'm going to use mini batches, as a batch gradient descent. I'm going to have a regularization term, which we can add in here. So these are all elements which we will bake into the program, which we are going to develop. So in order to calculate and train a model, we need to set up these additional terms. We need to have a gradient descent approach, which we have discussed in project 1 as well. So in our network, if we have 64 input nodes, and then we have 50 50 nodes, and then we obviously have +1 here, which is the biases we need. So we are ending up with 3,250 weights plus biases. So in the hidden layer connecting with the output layer, we would then have 50 nodes plus the biases multiplied with 10 here. So we have 510 weights and biases in the output layer. So the +1 is for the biases. So these are the total number of parameters. And then we are setting up the matrix multiplication. So let's just go down here a little bit. So we have set up the data. We have the feed forward pass, which we discussed already. But then we have the back propagation. And in the back propagation here now, we are obviously feeding back the equations we have for the different variables. So in this particular case, what we have is that this is the derivative of the cost function. And in our case, it contains now the this expression, which we set up earlier, multiplied with the derivatives of the sigmoid function. So this is for the hidden layer. And if I now go to the output layer, this is then just going to be given by the weights and the biases, which we have for that equation. And this returns simply the output weights and gradients, the output bias gradient, the hidden weights gradient, and the hidden bias gradient. So these are the expressions which we wrote down by paper and pencil. And when we have that, we need to set up a learning rate, which is 0.01. We have a hyperparameter lambda. We find these gradients. So it returns the different the weights gradients, the bias gradient for the hidden and the output layers. And here you see just a brute force implementation of the gradient descent. So what you have there. Now, you're going to replace that one with the codes which you developed in project number 1. And in the exercises this week, we are essentially going to do what you see here. So if you do that, the quantity we are calculating is actually the accuracy. So the old accuracy on the training data is actually not impressive. And in this particular case, the accuracy is you counting the number of correctly classified events divided by the total number of cases. And what we got now is not something you would brag about. So as I said once, if you're invited to a party and this is what you have to present at the party, I don't think you will be invited again. Maybe that's not why nobody invites me anymore. Anyway, the thing which we do next is to add these different hyperparameters. And we will now run over many different learning rates. So let's just try to wrap up this case and just run it. And in this particular case, now we have a full class for with one hidden layer. We are setting up the epochs, the batch sizes, as you did in project 1. We set up and create biases and weights. We have the feed forward pass. We have the output part here, which is given by this function here, ZO, and this is the probabilities which we produce. We have the back propagation part, and we make the predictions. We do the training over the number of epochs and the number of iterations here, and then we can evaluate and test the model. So if we now just run it, you see now that we can define the accuracy here to just be the number of correctly classified divided by the total number of events. So here, I'm now setting up 100 epochs and 100 batch sizes, the batch size of 100, and I can start training my network. And this is the next one. I adjust the hyperparameters, so I make a loop over hyperparameters, and you can see now that the accuracy score on test set is not that bad. And now I run, in that specific case, I had only one value of the hyperparameter, eta, the learning rate, and one for the lambda. Now I can run over a whole batch of values. And if I do that, what we are going to see, and this is probably the last thing we do now, you will see that we are now running through different learning rates and different lambda values. This is a hyperparameter, which is given by an L2 norm in this case. And you will see that the values are not impressive. This is the accuracy. But then there will be an accuracy which can be pretty good. So if we just run through this case, just let it run, and then we make a plot, a heat map, and then we can pick out the values which are the optimal values. So let's just run through it. And if you have some patience, we will stop after we've done that. You can see now that when we increase the learning rate, the results are getting a little bit better. And this will just continue. And you can see now that we are getting a score on the accuracy score on the test set, which is getting closer to 90%. So for this type of data set, the best result you typically get is around 99% on the training. And the human error rate is roughly also, or accuracy is roughly 98% as well. So this is roughly doing as good as a human would do it. So as soon as it's done here, we are going to make a plot and then we stop there. So it should be there pretty soon here. So we are getting to a lambda. I think I have the last lambda value, because then you will see what the final result is going to look like. And in some cases here, it actually doesn't converge properly. So I think it's roughly, it should be pretty soon. So I will just show you the final plot here, and then it should be done. So I think it's roughly done now. It should have a 10, and then it should have a lambda value of 10, and then it should be done. And now it's done. And then we can visualize. And the typical visualization you will see now. So here you plot the values of the learning rate, and here you have the lambda parameter. So this is roughly 10 to the minus 3. And the learning rate here of 10 to the minus 2, you see that the training is perfect. So you get an accuracy of 1. And then you go down to the accuracy on the test data. And you can see that in this case, with this simple model, we are getting something like 96% for that specific case. So this was a very simple model. We didn't do too many iterations, but still you're getting something which is decent. So as I said, a human gets closer to 98%. And we will see that we can refine this with better gradient methods, etc., etc. Okay, so I'm going to stop here. We will practice in the lab. We will also discuss this next week. And then we're also going to look at implementations of this to solutions of differential equations. And that's actually a very hot, interesting field for us who do natural science. Okay. So see you at the lab, and thanks for coming.